Okay, let's see sort of where we got to. So here's our final version, right? And what have we done? We certainly added the pipeline registers. We've added lots of ways to rewrite instructions, right? And the way we've added to rewrite instructions is we can take an instruction, you can either replace it with a no-op or with a B&E. And there's very specific situations, okay, at each stage as to why we might choose a no-op and why we might choose one of these B&Es. And you should understand, why would I be putting a B&E in this stage? When would that happen? So you should say to yourself, okay, notice the control signals here. These are null control signals, right? So these are null control signals are basically selecting. They're the rewrite control signals, and we can either execute the instruction, rewrite it as a no-op, or rewrite it as a B&E, capture PC plus 4 and XP. And there's very specific situations in which we do all of those. And in fact, if we do something in one stage, usually the earlier stages are busily putting in no-ops to get rid of the instructions that will no longer be executed. Whew. Okay, so so the bypass muxes and then all of these rewrites, okay, in addition to the pipeline registers were added. What do we get for having added them? Let's loop back and try to remember why we put ourselves through this pain for close to 90 minutes now. I don't know, Chris. We needed lectures 22 and 23. You filled them with something. Should I think of it as a no-op? Were you filling our pipeline stages for us? What was the point of all this? Speed. Pipelining. The whole goal was to do the pipelining. And how do we get something to run faster? Because what we did is we take all the things that take time, we put them into separate pipeline stages so they can be happening in parallel. So if it took 100 nanoseconds to do all of this, our hope is that we've broken it into 5 20-nanosecond chunks. If we stand in the write-back stage, that would mean that once every 20 nanoseconds we're writing a new answer into the register file, which means that we're effectively executing instructions 5 times faster than we were before. That's the whole goal of the pipelining. Sounds good. How many, is it likely we've achieved exactly a 5 times speed up? Lots of people going like this, which is a good thing to be doing. Where might we have gone wrong? Why wouldn't we get a 5 times speed up? I was selling you this used car just a minute ago, and it sounded good. Yes?
Some of the pipeline stages might take longer than others.
Right. So what happened was that we haven't exactly divided the delay up. Right, so we might get a factor of 3 out of this, maybe. I'm just guessing now, but it's not going to mean only if the gods were really with us would we actually get a factor of 5. Could we get a factor of greater than 5? No, 5 would be the best we could do. Okay, we're likely to get, and then you say, well, don't forget, Chris, you've been no-opping instructions right and left. Remember when we no-opt instructions? Because of branch delay slots, because of the structural data hazards caused by the load data hazard where we had to sort of stall the pipeline. And so we're, not only are we not getting a 5x speed up exactly, but we're introducing no-ops now and then as our, the final solution to deal with instructions that we can't really think of something else to do with. We can't correctly execute, so we replace them with no-ops. And so the extra no-ops and things like that also, effectively slow things down, because they don't really count as executing the user program unless you guys write really dumb user programs. Yes, 700,000 no-ops. Okay. One last run. We started with a neat single, cycle execution beta. The diagram, to this day, I've given this lecture for decades, or the beta lectures for decades. I'm always amazed at how elegantly simple the beta, unpipelined beta diagram is. It's just got a couple blocks in it. If you went off and practiced, you could probably type a beta from scratch into JSIM in 15 minutes, right? A whole 32-bit RISC processor, right? So that's pretty neat. Okay. Then we started saying, well, let's make it faster. And the way we made it faster is we started pipelining it. So when we did a 2-stage pipeline, we get some increase in throughput, not 2x, but some increase in throughput, because now the time for the instruction fetch is being overlapped with the execution of the previous instruction, which is neat, or the execution of the current instruction is being overlapped with the fetch of the next instruction. Maybe that's a better way to say it. But we had to do some fixes because occasionally we ran across a situation, particularly after taking branches, that the instruction that was in the IF stage we didn't want to execute. Well, then we gilded the lily and went all the way to a 5-stage pipeline. And we had to add all these bypass paths because now the write back is happening to the register file cycles later, as the instruction actually has to progress all the way down to the last pipeline stage before the register file actually gets updated with the effect of executing that instruction. So that meant that earlier instructions that wanted that value had to get it from other places in the data path, which we could do almost everywhere, okay, except when we wanted memory data in the case of a load instruction. So now we had to start freezing the RF and IF stages and put bubbles in the pipeline, little no-op bubbles that trickle down to the ALU, mem, and write back stages. Okay, until the load gets to the write back stage, and now we can get the data we want. Okay, then we started looking into how to not only, so that was normal execution, and now occasionally we had to make sure that we could capture the PC+4 value, so we've started figuring out how to do that. And in particular, if there's any sort of faults, we have to rewrite the offending instruction to capture PC+4, and then everything else earlier in the pipeline has to be flushed, meaning we have to actually rewrite them as no-ops. Interrupts, things were looking pretty until we remembered that we had to leave room for capturing PC+4, so a little fooling around with the XP register value got us that fix. All this extra hardware. Overall, what do you think we've done to the size of a machine as it went from an unpipelined beta to a pipeline beta? Look at this diagram. You say, look at all the registers and multiplexers and extra data paths, and compare them in your mind to the sizes of these other things. Right. Of course, if the ALU has a multiplier, that's a pretty piggy piece of electronics. It's just a lot of gates. But without the multiplier, these things are probably comparable in size to the pipeline registers. To all the other pipelining hardware. So the pipelining hardware is a significant increase, maybe a doubling of the actual number of transistors you have to buy, leaving aside the multiplier costs. This is very rough sort of seat of my pants sort of guess. So pipelining was not inexpensive in terms of transistors, but we got maybe a factor of 3 or 4 in terms of execution speed, which in the modern era of Moore's law, with transistors becoming less and less expensive half as expensive every 18 months, we have lots of transistors to spend. So this was not a bad investment.